So here, the PN junction is always kept reverse biased and forward biasing strictly avoided. Therefore, the current gate current is negligible. Thus, assumes to be zero. Hope this point is clear. We always keep this PN junction reverse biased. We never forward bias it. So when it is reverse biased, there is a very small current, right? A very small leakage current. We can assume that there is no current at all. Okay, so the gate current is zero. And here, when VDD voltage is applied between the drain and the source terminal, drain current ID is set up along the channel. But since the gate terminal is kept open, the JFET act similar to a resistor. So here, this gate terminal is kept open. Therefore, this one just acts like a resistor because it is not going to reverse bias. It is not going to reverse bias this junction. It will act just like a normal resistor. Okay, this is identical to this resistor, but here the potential continuously drops. You must have that idea. Okay, it continuously drops, but there won't be a reverse bias because this gate is kept open. Now let's connect a source. Now we are going to connect a source across VGS. So when VGS is zero, the voltage VDS is supplied between the drain and the source. Current flows as shown. Okay, the voltage drop the voltage drop caused by the current reverse bias the PN junction. So this point we already discussed, right? Since the P region is heavily doped than the channel, the depletion layer penetrates more into the channel as shown, wedge shape. Wedge shape. So this point also we discussed why it penetrates more and why we get a wedge shape. The depletion layer does not have any charge carriers to conduct the current. This is a fact we already know. The width of the depletion layer gradually decreases from drain to source. Therefore, reverse bias voltage is higher close to drain when compared to source. The width of the depletion layer gradually decrease from drain to source. Should it be the other way? Source to drain. Oh, sorry. We are talking about the depletion layer, right? The width of the depletion layer is greater closer to the drain and smaller closer to the source. Okay. So that is what is mentioned in that point. The width of the depletion layer gradually decreases from drain to source. Therefore, reverse bias voltage is higher close to drain when compared to closer to source. We discussed this. When the applied external reverse bias voltage is increased more and more, the width of the depletion layer too increases. And now let's talk about this point. These 3 points. Now here it's mentioned when the applied external reverse bias voltage is increased more and more, width of the depletion layer too increases. Next, for a certain value of VGS, width of depletion layer equals the width of current, preventing any current flow. And we call this as VGS off. Finally, when VGS is increased, the drain current is reduced. When VGS is zero, minimum reverse bias is observed, therefore depletion. Okay, let's discuss these last few points. Have you copied these 4 points? Sir and Sajad, did you copy those 4 points also? Okay, so there, what they have mentioned is, now let's say we are going to increase. Now we kept this one at 0, right? We kept this at 0 only. We discuss what is happening. Now what we are going to do is, we are not going to keep it at 0. We are going to slightly increase it. Let's say I increase this to 1 volt. If I increase this to 1 volt, this is already grounded. Then gate terminal will have -1 potential. So here, instead of 0 volt, initially we had 0 volt, but now it's going to go to -1. What can you tell about this reverse bias? Has it got stronger or weaker due to this voltage? Has it got stronger or weaker, this reverse bias? It will get stronger, right? Because when we have more negative potential to p-type, it is going to get reverse biased even more. So when I'm increasing this voltage, -1, -2, -3, -4, when I'm increasing this voltage, when I'm increasing this source, uh, the voltage at the gate is reducing. So when it is reduced to the maximum value, where this channel is so strong enough to close this channel completely. This channel is now completely closed. There might be a very small leakage current. Other than that, it is almost closed. So for that value here, when I'm this is VGS 0, this is VGS is equal to 0. And if I increase the voltage, if I increase the VGS voltage to 1, gate respect to source, gate respect to source, if we increase this supply, then the current will reduce. The current will reduce. When I increase further, it will even further reduce. For certain VGS voltage, for certain VGS voltage, it is almost 0. It is almost 0. So this VGS voltage we call as VGS off. This, if you apply this voltage, it will completely shut down the current flow through this. So uh, that is mentioned. That is mentioned in these 2 points. When the applied external reverse bias voltage is increased more and more, the width of the depletion layer 2 increases. For a certain value of VGS, the width of the depletion layer equals the width of channel, preventing any current flow from drain to source. The value of VGS is known as cut-off voltage or VGS off. When VGS is increased, the drain current ID reduces. So that's obvious, right? So are you clear with these 3 points? First, second, and third, clear with them. And the final point, VGS equals 0. VGS equals 0. That is the minimum reverse bias voltage I can apply, right? That is the minimum reverse bias voltage because I won't forward bias this. So minimum reverse bias is VGS is equal to 0. For VGS is equal to 0, it is observed the width of the depletion layer is minimum. This is the minimum value we can get for the depletion layer, and the conducting channel is maximum. Thus, ID current is maximum. This is designated by IDSS. Okay, ID current saturated. So here in this graph, this current over here, that is IDSS. Okay, up to this, it's clear, right? So next topic, Output characteristic. Output characteristic. ID versus VDS. So so here this is for VGS is equal to 0. For VGS equal to 0 only we get the maximum current. And this voltage, where the voltage becomes constant, sorry, where the current becomes constant, we call this VDS voltage as the pinch off voltage. We call this as the pinch off voltage. Pinch off voltage. So you can think just like, what do you mean by pinch? You use your two fingers to pinch, right? Between this region you are going to pinch. So it's just like this two depletion layer, these two depletion layer together pinching this current. So that is why we call, that is how this name is given, pinch off voltage. So this is the pinch off voltage. Pinch off voltage is the voltage where the current become constant when VGS is equal to 0. That is very important. And here in this region, we get a straight line. We get the y equal mx straight line. So we call this region as the ohmic region. This part is the ohmic region, and beyond this line, it is the saturation region. So region After this yellow color dotted line, that region we call it as the saturation region, saturation region, or the pinch off region, pinch off region. And on the other side, this region we call it as the ohmic region. It behaves like a ohmic conductor, ohmic region. When we continuously increase the current, when we continuously increase VDS, after a certain value, it will uh, break down. It will undergo a breakdown. So we cannot increase the voltage forever. The current suddenly increases. After that, it is spoiled. So this part, we call it as the breakdown region. Breakdown region. And this dotted line, this yellow color dotted line, it is the variation of VDS for pinch off voltages, or for pinch off. So here this action at each and every point, we call it as the pinch off. But when I say, when we denote pinch off voltage is special for VGS is equal to 0. You must get the clear difference. Where the current becomes constant, we call them as pinch off. It doesn't matter what the value of VGS is. But when we say pinch off voltage, it is the voltage at pinch off when VGS is equal to 0. I have drawn the graph. And is the graph clear? From 0 to from 0 to few volts of VDS, few volts of VDS, the current increases as determined by Ohm's law, as determined by Ohm's law. Therefore, the region is called the ohmic region. The ohmic region. The ohmic region. When VDS is further increased, when VDS is further increased, due to widening of the depletion layer, channel resistance increases. Channel resistance increases. Thus, the drain current Thus, the drain current tends to become more horizontal and constant. More horizontal and constant. And constant. This is known as this is known as pinch off condition. This is known as pinch off condition. When Vgs is equal to 0, when Vgs is equal to 0, the value of VDS, the value of VDS at which pinch off condition, at which pinch off condition is attained, is attained, is known as, is known as pinch off voltage, pinch off voltage, VP. The region where the region where VDS is greater than VP, VDS is greater than VP, is the pinch off region, is the pinch off region or the saturation region, or the saturation region. Where ID remains constant, where ID remains constant. When VDS is increased, when VDS is increased beyond a certain voltage, beyond a certain voltage, VBR, beyond a certain voltage VBR, the FET gets damaged. The FET gets damaged. Gets damaged. So it cannot be used again. So it cannot be used again. So it cannot be used again. This region is referred as the breakdown region, as the breakdown region. Once you have completed, let me know. Saja, how about you? Completed. Okay. Next, transfer characteristic. So here the transfer characteristic is between ID and PGS. So when we are drawing between ID and VGS, let's get the help of ID graph also. So here, first let's draw the ID graph, ID versus VDS. Okay, so take half of this and the half of this. Now get this value over here. For VGS is 0, for VGS 0, we get this value. Okay. For VGS is 1, we get this value. For VGS is 2, we get this value. And for VGS is equal to 3, 0, 1, 2, 3. And for VGS is 4, it's 0. And now you can plot this curve. So that will be the transfer characteristic. This is VGS. Zero, one, 1, 2, 3, and 4. So it's going the negative side. The variation of ID versus VGS is given by is given by the equation ID is equal IDSS 1 minus VGS over VP whole thing square. Okay, this is the equation. Leader copy the graph. Sarah, done. So this is the graph, and this is the equation for that graph. Then IDSS drain current ID for VGS is equal 0. VP, that's the pinch of voltage. Pinch of voltage that's the pinch of voltage, or we can tell that's the VDS for VGS equals 0, or VDS for VGS equals 0. Next we have VDS for VGS equals 0 when ID is constant. When ID is constant, then only we get the pinch of condition, right? IDSS comma VP is a constant for given JFET. So in BJT, we had a linear relationship, right, between IB and IC, but here we don't have such a linear relationship. In contrast to linear input-output relationship, in BJT, so what's the relationship there? IC is equal beta times IB. Input-output characteristic, input-output characteristic is non-linear for JFET. Next point. When VGS is equal to VGS off, when VGS is equal to VGS off, then we know that current ID is 0, right? ID is equal to 0. So if ID is equal to 0, we know, uh, but ID is equal IDSS 1 minus VGS over VP square. So this has to be 0. For this to be 0, no, IDSS cannot be 0, right? VGS over VP has to be equal to 1. Therefore, VGS over VP is equal to 1. So VGS is equal to VP. Now here the value. We are taking the values, okay? So mod of VP is equal to VP. Mod of VGS is equal to VP. VGS, we know that VGS is less than 1. Now here, let's take VGS off. VGS off, the mod value of VGS off is equal to mod value of VGS off. But we know that VGS off is less than 0. That means it's a negative value. So VP is equal negative of VGS off. Or VGS off is equal to the negative of VP. VGS is anyhow negative, right? So VP is positive. If you want to have VGS negative, then we will have to multiply it by a negative in front. Okay. Here we only apply the value, not the sign.